All right, let's look at one more example here. And this one, I'm going to take the time to go through all of the algebra stuff with this one. We've got an equation of ellipse that we're going to need to be using, but it's not a particular ellipse. Like if I had something like x squared over 4 plus y squared over 9 equals 1, that would be a particular ellipse. But here I have more of the general form for the equation of ellipse. And I'll talk about that a little bit in a second. But this is going to be an opportunity for us to see how we can come up with a more general equation for what the optimal scenario should be. So in this problem, pure geometry problem, pure math problem, we're looking at finding the area of the largest rectangle that can be inscribed inside the ellipse with the equation x squared over a squared plus y squared over b squared equals 1. And so I want to talk about just like, what does that equation represent? Where does it come from? And what does it mean to inscribe a rectangle inside of an ellipse? Like, what does inscribe mean? And I encourage you, like, as you're thinking through, any problem that you see in front of you, like one of your first steps that should always, like, whether you know everything that you're supposed to do in the problem or not, like, the first thing you should ask yourself is, do I understand every single word, phrase in the question? Do I understand the question? Before thinking like, what should my first step be? You should really be thinking like, do I even understand what the goal is? And are there any words or phrases that are making this confusing to me as far as what I need to be doing? So here I want to take this opportunity to talk about the word inscribed and explain where this equation of an ellipse comes from. So if I have just x squared plus y squared equals 1, this is our standard Pythagorean theorem. And let's see, this is going to be 1 second here. Okay, so I've got my ellipse tool sorted out here. Let's make that look a little bit nicer. So x squared plus y squared equals 1 is just our standard equation of a circle. So if this is the point x comma y, then the radius of this circle is 1. There's our x value, our y value. And so we can get our Pythagorean theorem here, x squared plus y squared equals 1. Now, if I take the ellipse equation and rewrite this as x over a squared plus y over b squared equals 1, this is inside stretches on x and y, or let's say on x by a and on y by b. So what this is going to do is it's going to take and give us an ellipse where now x direction has been stretched by a and the y direction has been stretched by b. So here we still have our point x comma y, but by using transformations we can just see how the original circle has been stretched into an ellipse in this manner. Okay, so that's where this equation is coming from. And the next thing we want to ask is how to inscribe a rectangle inside an ellipse. So before I even talk about that specifically for this problem, more generally, if I wanted to inscribe one shape into another, that means make it as big as possible inside that other shape where the corners, the vertices of that shape are touching. So here this is inscribing a rectangle inside a triangle. That's not a good ellipse. That's not either. Let's just use the one that's over here. Okay, so if I wanted to inscribe a rectangle over here, I would push it as big as possible, like this. Okay, so this is an inscribed rectangle. We can inscribe rectangles in different ways. I could make it thinner. And a bit taller, or we could make it really wide and shorter. But we see when we do this, no matter how we do it, there's a lot of symmetry going on in how we inscribe these rectangles inside the ellipses. Okay, let me draw this again and try and clean it up, and we want to sort through what we're doing here. Okay, so I've redrawn my ellipse with a single inscribed rectangle inside of it. Here's our point x comma y. This distance is a. This is the a equals the x radius, which is not a formal term at all. You won't normally hear that. This is the major axis because it's wide, but it's the, let's call it the x stretch. That's fair. Radius really just works with circles, and I don't want to use unconventional terminology here. B is the y stretch. So this is B here. So what are we trying to maximize? We're trying to maximize the area of the rectangle. And so the area of this rectangle well, it's going to be a length times width again. But we need to understand where we want to pick this point here for this to all be a maximum area, right? So our constraint is the fact that we're inside an ellipse. It's inscribed in the ellipse. So we have that the rectangle must be inscribed in the ellipse, which is x squared over a squared plus y squared over b squared equals 1. Our constraint equation was actually given to us straight away in this problem. So it's kind of one of those things where it's so right in your face it can be easy to miss, right? So anytime you're given an equation like a formula within the problem, that is most likely your constraint equation. So just be aware of that as you're going through and doing the exercises for the lab and for the homework, that could pop up, and just don't let it be something that you overlook, just that you are going to be using that given equation in some way. So the length is here, and the width is here. And I want to get everything in terms of, say, x. So we're going to try and get it in terms of here. So the length is going to be 2x, because x is half the distance of this, and then the width is equal to 2y. So if we put those in to our area formula, this becomes 4xy, but we still have these two variables, x and y. So I want to eliminate one of them, and we're going to do that by taking our constraint equation and solving for, I'm going to solve for y, so everything is in terms of x. So I'm going to start by multiplying, let me just rewrite this. I'm going to start by multiplying both sides by b squared. And that's just to clear out that little denominator there. Sorry, I'm going to change my mind. I'm going to just subtract that x squared over a squared to the other side first. And then we'll multiply by the b squared. Y squared over b squared equals 1 minus. Now multiply times the b squared. And then we need the square root of all of this. Actually, let's do this. Let's keep that b squared factored out. Because I'm about to take a square root, so that'll be nice because it just becomes this. Put the b in front, b square root of 1 minus x squared over a squared, like that. Okay, so I'm going to take this and plug it back in for y, for x times b square root of 1 minus x squared over a squared. And this is now a function of x. Now our domain on A is going to be, we're going to just stick with the point that we're using to be in the first quadrant, right? So we could inscribe our rectangle where that top right point is in some different locations, but we're just focusing on that top right point that's going to create our length and our width. So the domain here is going to be 0 for x all the way up to a. And from this, we're going to start going through our whole derivative process. So we're going to get into a whole lot of algebra here. So let's take this nice and slow. A of x equals 4b times x times 1 minus, I'm going to write this as 1 over a squared x squared, just because this is going to help us with our derivative taking. And then we get our derivative. And you can use software for this, and it's just like how it organizes things may or may not be the best, but don't be afraid to try and use that. The 4b is a constant. And so this is a product rule. This is my first and my second. Derivative of the first is just 1 times the second plus the first times the derivative of the second. And we're going to need a chain rule on this. So the derivative of this inside is negative 2 over a squared x to the first. So I'm going to set all of this to 0 and start cleaning it up as best I can here. Let's see, so this first term, I think we'll just leave that alone for a moment. Over here, that negative 1/2 is going to push that into the denominator. So I'm really thinking of this as like what's on top, what's on bottom. We've got this minus term over here on the right. So the whole thing's going to be a subtraction. And I've got a fraction bar. The 2 on top and bottom can cancel. So that's not so bad. We're going to have 4 bx squared on top. So the 4bx in the front and then the x all the way off to the right side there. And on the bottom, we're going to have a squared and a square root of 1 minus 1 over a squared x squared. And we can then move this to the other side. And then we're going to multiply both sides by a squared square root of 1 minus x squared over a squared over 4b. And this allows us to cancel the 4b on both sides. And then everything on the left is going to cancel out except for that x squared, which is nice. And then on the right side, we'll have the a squared still, but then the two square roots will cancel, leaving just the 1 minus x squared over a squared. And that's really nice because now we have x squared equals a squared minus x squared. We can add this x to the other side and get x squared equals a squared over 2, or x equals a over the square root of 2, and if we rationalize that denominator, a root 2 over 2. Fun. So go ahead, slow that down if you need to. Go back, rewind, pause, just stare at it. So that's our x value. Pause, I want to think about something. So I need my y value as well. So if this is x, then I'm going to take this and I'm going to plug it in for y. So y equals b square root of 1 minus x squared. So I'm going to use the x squared actually right here. So we're going to have a squared over 2 over a squared. So a squared over 2 over a squared. This is, it's over 1. That's a squared over 2 times 1 over a squared. That's just going to equal a 1/2. So this is, oh, you know what? I'm going to, so I keep going here and get the right answer, but let's actually use something that's going to avoid all the square root stuff. So I'm going to use this y squared right here. So y squared equals 1 minus x squared over a squared times b squared. And then we'll plug that x squared in. And the a squareds cancel, leaving 1 minus 1/2 b squared equals b squared over 2, which is nice that we've got this wonderful symmetry in our answer. Let's take that square root. So y equals b over the square root of 2, or b root 2 over 2 if we rationalize. Okay, let's go back. We're trying to find the area of the largest rectangle, and the area is going to be 4xy. So this is going to be 4 times a Let's do it in the unrationalized forms for this part. A over root 2 times b over the square root of 2. And this is 4 times ab over 2, which is 2ab. And that's just a great formula right there. So we can say, without having to redo this for a lot of different ellipses separately, if we have the equation of an ellipse, we can just say that the area of the largest inscribed rectangle is going to be 2 times that a value times that b value. And that's it. So rather than, I could give you one problem where you have to start from the beginning, where a is 3 and b is 2 or something like that, and then you have to go through and do the process. Then you get another problem where a is 5 and b is 7. You have to redo the entire process again. But by doing it this way, where we are generalizing a and b, we now have a formula at the end for inscribing in any ellipse. So that's just super powerful. And we can write a conclusion out that says the rectangle of maximum area that can be inscribed in the ellipse x squared over a squared plus y squared over b squared equals 1 has its upper right vertex intersect the ellipse at a over root 2 over 2, or a root 2 over 2, comma b root 2 over 2. Its width is a root 2. Its height is b root 2, and its area is 2ab. All right, so there's a lot there. Go back. I do recommend rewinding to any part and kind of like figuring out how all these pieces are coming together, like seeing the end and then going back to the beginning and seeing what steps I took can kind of help you see what was motivating me to make some of the moves that I did. So don't be afraid to go back to some of the earlier parts and then be like, okay, why did he set it up this way now that I've seen how the whole puzzle kind of comes together here? And once again, do take a look at these steps and see that I am still following all of these steps as I went through this problem. And with that, I will call it an end to this lesson, and we will, you are responsible to work through those lab problems on your own there. See if you can't find a study group and work on them with each other. I am, again, willing to, if you get a study group together and you're all working together, tell me the time, the location that you're at, how much time you worked together, and I can give you a couple of extra credit points for doing that on this assignment. Okay, thanks everyone very much. Have a great day.